My name is Matt Cooperholtz, and I have been in a deep and meaningful relationship with computers since we first met in 1979. And when you've been in a relationship for close to 40 years, you know, people ask, well, how do you keep the passion? How do you keep the relationship alive? And the key is you keep doing new things together. And at the moment, my passion with computers is around blockchain technologies and data mining to algorithmically provide trust based on the data on them, which we're not going to talk about today. When I was a kid and you're good at maths and you want to do business, you become an actuary, because data science didn't exist yet. And I also studied computer science at uni, where I majored in AI. In those days it was programming in Lisp and teaching computers how to play games. But my girlfriend was a neuroscience student, and I went probably to more of her lectures than mine. And I guess today is a culmination in 25 minutes of 25 years of fascination with intelligence and artificial intelligence and business consulting. So I left the actuarial firm for a startup which had AI software in the late 90s, and in the crazy environment of a startup was applying it in anger to real world problems, often going head to head with the traditional statistical approaches I was more familiar with. And since then have been in the land of professional services, solving big, complex, juicy problems for our clients around the world in all manner of industries. My boss, John Studley, was the bloke who asked the question before. He's the head of analytics in Australia. So, John, just chuck your hand up. If I don't make any sense, because I get a bit excited about this, John can translate. If you think I did a good job, tell John. If you think I did a poor job, also tell John. The talk today is about practical artificial intelligence. But I think we've got to start by asking, what do we mean by intelligence? And then how can that be artificial? And in the back half of the talk, I'll move from this sort of theory, which is probably going to raise more questions than it's going to answer, into how you should be practical. And it's not just how you should be practical with artificial intelligence, it's how you should be practical with analytics, in my opinion and my experience. And I'm going to relay that to you through, I've picked ambitiously 8 war stories from hundreds and hundreds, and hopefully these stories will give you a little bit of an inkling how that process, it's less about technology and more about process, allows you to really give demonstrable, scalable, reusable results in this field. But to start with, let's consider what is intelligence? It's a good working definition is anything that takes inputs and adaptively produces some output. Now, by that really loose definition, molecules display intelligence. RNA, DNA, complex chains of amino acids, put enough of them together, and you've got plants. And if you've ever watched David Attenborough show you fast forwarding of plants, it's clear that they are responding to their environment and communicating with chemical messengers. But typically in the field of AI, we start to think about weak AI or a narrow or applied form of intelligence. And we'll talk about that to start with before moving into the concepts of general intelligence, and then above that, human intelligence, or perhaps the intelligence that only comes with some form of consciousness. The easiest narrow intelligence is teaching a computer to play games. And you teach a computer to play games by graphing out every possible move that can occur, and making a decision, so some sort of evaluation to adapt to the input of what the human's done. And with tic-tac-toe, there's only about 64,000 combinations. It's a 9-move game. We could knock it out in Excel in about 10 minutes. But if you look at something like chess, where there's 10 to the power of 123 different games in a chessboard, that's more than the number of atoms in the known universe is the combination in a chessboard. So you can't just brute force it. You need to be cleverer with your heuristics and your pruning and the decisions and maybe even your learning. But in 1997, when the unthinkable happened and the then world champion Garry Kasparov was beat by a purpose-built piece of machinery from IBM called Deep Blue, we said, oh, no, that's not genuinely intelligence. It was just a really, really fast computer. Genuine intelligence would be beating a computer at Go. Because if you think chess is complex, the game of Go has 10 to the power of 360 combinations. So if you took every atom in the known universe and expanded every atom into its own universe and then counted up all the atoms you have together, you still don't have the number of games on a Go board. But last year, a computer, DeepMind, a company since acquired by Google, which pioneered sort of deep learning and a new novel use of neural networks, instead of brute forcing this game tree, found a way for two different neural nets, a short-term one and a long-term one, to compete with each other. And it learnt from human games, and it learnt from playing itself, and it beat one of the best humans in the world at Go 30 years before we predicted that a computer would be able to do so. And I love the Google engineer, or executive rather, who introduced that competition. He said, no matter what happens today, it's a fantastic victory for mankind. Another form of general intelligence that we come across, narrow intelligence that we come across all the time, is the recommendation engine. If you bought this, you may also be interested in that. It's a way to make a lot of money. It's what we see on Amazon and eBay and all kinds of advertising. You're trying to figure out, I want to know you so that I can offer you the thing you're most interested in. And before they got into streaming media, because it didn't exist in 2009, Netflix was a DVD company. And I'm telling this story not only because some fancy form of forests using boosted gradient trees ended up being the best way to predict what movie you'd like if you also liked another movie, but because it harnessed the power of mind plus machine. The best chess player today is not a machine, it's not a human, it's a centaur. It's a bunch of humans and machines working together. The best algorithms came from the gamification of data mining. These guys pioneered it by putting up $1 million and got the crowd to compete, and you got the best of human efforts smashing through their previous predictions by 10%, followed closely by Kaggle in 2010, who crowdsourced and gamified data mining and proved that the best human minds together with the best algorithms can beat previously held records in things like identifying dark matter or predicting protein folding in relation to HIV. And we say, okay, granted, there's some narrow intelligence, but what we really mean is general intelligence. When is a computer going to display that? Well, we use it every day. Famously in 2002, before their IPO, the editor of Wired magazine, Kevin Kelly, asked Larry Page, why are you building another search engine? There's no money in search, which was not entirely correct. But Larry Page said to him, we're not building a search engine, we're building an AI. And if you think about it, every time we use Google, we are teaching it. When you search for an image but you click on the third one, it realises that's probably what you meant. It realises that when I search for something, I'm looking for something different to you. And if you're using a Google device that's also looking at your calendar, your GPS and your travel histories, it's intelligently making suggestions that you should leave now because you're going to be late because there's traffic in the way. So what an amazing general purpose engine. And the really important question to consider, that are we searching it or is it searching us? But sometimes we want to get a little bit anthropomorphic with regard to general intelligence. We say, no, it's human traits like seeing things. A computer will never be able to read text, they said before OCR proved that it was possible. Okay, I can do that. It can't read handwriting. Of course it can. And nowadays, the close to 2 billion Facebook users, that's more than a quarter of the people on this planet who are active users of Facebook, have trained it so that you can put a photo in and it knows exactly who that is. So the facial recognition is through the roof. Now, if that's not a fantastic global intelligence on image searching, and the deep learning now in something like Google Photos, you upload all of your photographs and you can say, show me a photograph with a bicycle taken near sunset in Melbourne. That's a fantastic contextualised search, and machines are doing it in their stride. The ability to hear and understand what's being said, not just speech recognition or voice stress analysis, but Shazam, what's that song? I want that at home. And it's a noisy bar and it still picks out the song through sound recognition. And there are other apps that you can hum or sing the song even off key and it will suggest it to you. Now, it's a pretty interesting, narrow, general-ish form of intelligence, and the ability to interact with us. I mean, look what Siri did and what other intelligent assistants are now doing in terms of a plain English question, a plain English answer. What about something even more general? Driving a car. You've got to see, you've got to process, you've got to make split-second decisions, you've got to not be distracted. If there's going to be an accident, you've got to take the path that has the least overall impact. Well, my dad's Tesla is driving itself. And whilst it was a long time ago in 2011 that the early version of Watson beat Jeopardy by hoovering up all of Wikipedia and a few other things and being able to take an answer and suggest what the question is, IBM have continued with their technology in the form of cognitive intelligence that you put in corpuses of documents and you ask a general question in plain English and get an answer. Well, that's the intention anyway. And what's actually happening here is a bundle of different technologies. There is parsing of language. There is structuring unstructured documents. There is clever search and retrieval. But all of these things are clearly well within our reach. So what is it to be artificially intelligent? If we've done all these things and we thought they once were it, but now we no longer do, we keep moving the goalpost, right? The original goalpost was set by Alan Turing, the father of modern computing, in a seminal paper on 1950 with a thought exercise of can computers think? And he realised that was too difficult because, as we're finding, defining thinking and intelligence is pretty hazy itself. So he said, can a computer imitate a human to the extent that you think they're thinking? The imitation game. If there's a person in one room on a terminal and they can't tell if they're talking to another person or a computer, then that computer, in general chit-chat, is regarded as artificially intelligent or having passed the imitation game. Well, in 2014, Eugene Gustman, a 13-year-old boy from Odessa in the Ukraine who's got a guinea pig and whose father's a gynecologist, successfully fooled more than 1 in 3 judges to thinking that he was human in a 5-minute competition. So we actually have passed Turing's test for intelligence, but again we move the goalpost and we say, no, that's not it. What we're talking about as human intelligence or very strong AI is the inherent, basically, simulation of the entire human brain. Now, again, we want to project onto computers the way that we think, but we've evolved this way. It's a messy thinking process that was successfully helped us get to where we are as a species. But if you just indulge me in a quick experiment, and it's only going to take 10 seconds. If you close your eyes and feel your feet on the floor and the chair against your back, and just take 10 seconds to listen, the observer, listen to what your mind is saying. Pretty random and chaotic in there, isn't it? I did that for 10 days once in silence, and yeah, it's hard work. So why would we wish that upon a machine that we're trying to use to make our life easier? It's just not a very practical way to evolve artificial intelligence. It's a great way to get off the planet as information, or it's a great way to live forever inside a computer, but in terms of practical AI, solving business problems, it's not the way I'd recommend. So it concludes this first bit by saying, look, if you think you understand intelligence or artificial intelligence, then you probably don't understand it. So I'm not sure I've really helped. I'll tell you what I mean when I talk about solving problems with artificial intelligence. But first I want to discuss a couple more phenomena because I think they're really relevant to everything we're going to talk about today. The first one was coined by Gordon Moore, the father of Intel, in 1965, where he predicted that the number of the number of transistors on a chip is going to double. He initially said every year, then he said every 2 years. And this sort of exponential growth has been observed not just in processing power or processing power per dollar or solid storage or moving storage or storage in general, but also in communication speed and connectivity and networking and pixels in a digital camera array. So everywhere seeing this incredible acceleration, which is why some things that have always been around, like AI, it's been around since the 60s, feels like it's brand new. The other one is Amara's law. Roy Amara said, we as a species tend to overestimate the effect of technology in the short run and underestimate the effect of technology in the long run. And what that leads to is the so-called hype cycle, followed by the trough of disillusionment. Now, AI had its famous AI winters through the 70s and 80s where we were deep in the trough of disillusionment. But what actually was happening was continual progress on algorithms combined with computing power that meant that AI has never gone away. It's always been here. We're just hearing a lot more about it. Another thing that isn't new is the fact that data is constantly increasing in its volume, in the velocity with which it comes to us, and in the variety of the different data sources. So it's great for us as practitioners that everyone's talking about big data like it's something that's just arrived. But solidly for the last 25 years, I've been working with ever-increasing size and variety of data sets. Similarly, the idea that all of a sudden there are these robots that do things they couldn't do before. I mean, come on, guys, it's just scripting. It's writing code. We've been doing it for a long, long time. It's in the common vernacular and everyone's excited about it, but it really is, a different point on that hype cycle. It's a very relevant thing. All of these things working together are going to completely change the way the world works. The increasing connectivity of devices. Now, I'll give it to you. This genuinely is new, which is a function of the decreasing cost of sensors and increasing technology and the wider IP namespace. And something that genuinely is new is the Internet of Trust. The ability to use maths in a way to have a public and decentralised ledger and exchange of value. You put all 5 of those things together, and there's incredible effects coming up for humankind. So what do I mean when I talk about AI in a practical sense? Machine learning is a subfield of AI. Technically, whilst both a statistical technique and a machine learning technique, linear regression, good old linear regression, is artificial intelligence. Now, that's not what I'm talking about. It's pretty hard to draw these boundaries. So I'm talking about a range of techniques which might be supervised, you're training it on something. Unsupervised, you're asking it to train itself and look for patterns. Semi-supervised, somewhere between the two, that utilises feedback loops, continual improvement, often based on artificial neural networks. In other words, non-parameterised, non-linear regression techniques. You may be using association rules or putting them together with probabilities for Bayesian networks. Multiple neural networks chained together called deep learning. Other forms of machine learning like support vector machines, and quite often advanced approaches to time series analysis. These are some of the war stories I want to share with you. But above and beyond, as Mark said, above and beyond whiz-bang techniques, a solid analytic process is the most relevant thing to helping your organisation scale and become truly analytically enabled. And the key to that is not to start with a novel analytical or technical challenge, but rather to start with a business challenge. Where are you going to make money? Where are you going to reduce risks? Where are you going to save money? Who are the stakeholders? Who's backing this? Where's the whole thing at politically? What are the potential derailers? How long have you got? What's the budget? Good old-fashioned, traditional consultative approach to identifying the business challenges with the clearest bang for buck where the improvements can be measured. Only at the back of that do you get an analytical problem statement, and that's when you should look at the data. And this is a very simplified version of what we use around the world, which is a customisation of CRISP-DM, which was introduced before. So the second step, understanding the data. Not just your own internal data, often in disparate systems, often imperfect. I've only had one client that I would say had perfect data. It was a small bank that had built its systems from scratch, and it was perfect. Everything linked, one system for everything. Everyone else, it's all over the place, and that's okay. There's still value in it. You can still join it together, and the war stories I'm going to share today are mostly highlighting how you bring data together for better overall gain. The data might be structured or unstructured. If it's unstructured, you've got to structure it. It might include structuring videos, or looking at pictures, or changing recorded text to speech and then extracting the features from it. The data might also be external data. There's great value in linking the two, or more currently now, especially if it's a customer-facing problem, social data. So we did some really interesting work for an insurance client, predicting who was going to claim or churn simply by looking at the policyholder's Facebook page. The third step, analysis, which has the 3 sub-steps of preparing the data, applying the technique, and then evaluating it. And the fourth step, the most important, deployment. You've got to do something with it. It's got to make change. When you define the challenge in the first step, you've got to be looking forward to the fourth step. Is this going to show up in the cab of a garbage truck to tell it to turn left or right, so you're optimising the pickup route? Is it going to change the way a call is routed in the call centre? Is it going to affect the language in a direct marketing campaign? Unless you have a view to deployment, all the rest is a waste of time. And unless you start with a meaningful, carefully ranked and chosen business challenge, all the rest is a waste of time. So AI is deep in that third sphere of analysis, including how you prepare the data. But the first and the fourth step are the most important. So let's travel back in time to 2006, where for a large North American bank, they were facing the challenge relating to their customers. And many of my early war stories are to do with customers, because all of our clients have customers. And their challenge was, we're about to run a massive campaign. We need to upsell, cross-sell. We need to retain the ones which we think we're at risk of losing. We need to acquire new ones. And we need to really have a deeper understanding of our customers. But our data is all over the place. Now, we merged external data. This was overseas, so it was a different type of statistics, but basically geospatial statistics merged with every transaction every customer had ever made through every channel, including physical channels in branch, ATMs, credit cards in stores, over the phone. We looked at that temporarily, and it's still, even though it was in 2006, one of the largest models I productionised, in that it had 17,000 metrics simultaneously considered for some 10 million customers through a range of both supervised and unsupervised artificial neural networks. The deployment, however, outside of our high-powered lab had to be in fairly antiquated systems at the bank. So we had to translate these deep insights into 42 campaigns that we're going to continually improve by working them back to if-then-else rules, in other words, decision trees. Airlines were other industries that had antiquated systems, and I've done this both in-sourced, outsourced, co-sourced for many years, only for a couple of months for different airlines around the world. And the reason why they have such antiquated data is because you built these systems in the 60s and you've been flying every day since then, so how do you tear it down and start again? A lot of old green screen mainframe environments. The challenge they're facing was also to do with their customers, but airline customers don't churn as obviously, you just see less of them. Every now and then you get a frequent flyer card chopped up back in the mail when you've really upset them, but generally they just vote with their feet. So how do we acquire the right customers at the right cost? How many flights should we be flying? Where should they seat? When should we promote them? How does all this relate to loyalty and marketing and offers were some of the challenges they were facing. The data was the booking system, what they booked, what they paid compared to everyone else on the same seat, price sensitivity. When did they check in? Did they bring any bags? Did they go to the lounge? Have they called the call centre? Have they complained? Have they complimented us? Did we mishandle their bags? Airlines never lose your bags, they just mishandle them. What comments have been made on social media? Again, this wealth of thousands of metrics about customers joined to operational data. The best techniques available were from the fields of machine learning and AI, where we were able to really hone down into micro segments of customers and specific treatment formula. The deployment into these antiquated systems was just a tag into a spare field. But it was updated every month, and customers' journey through those tags were tracked, and it would change the way you were handled in the front line, on the aircraft, at the booking time. The customers we don't want, and especially in a post-9/11 world, and in a world where the regulator is asking us to be more responsible with regard to what our data could tell us, is the detection of fraud. And I've done this for a number of banks and insurers and gaming agencies, both or around the world rather. And the challenge there is to make use of the wealth of data, the low-level transactional data, in order to find and stop the bad guys. And to Mark's point earlier about feature engineering, or step 3 in CRISP-DM, data preparation, or what I'm putting under the pink circle of analysis, the transaction data alone isn't going to get you much. But if you bend and twist it so that it exposes a network of related parties, and then you consider that as a weighted and directed network, and you apply social networking metrics, even things like Google's PageRank, which was designed to surface important web pages. Under the covers, it's a complex technique called eigenvector centrality. It turns out that analysis of the networks, quite often in both a supervised way, we know what we're looking for, but more interestingly for fraud, because they're clever, is the unsupervised way. By definition, fraud is behaviour which isn't legitimate. So it can't look like it's legitimate. And if you allow machine learning techniques to separate out what doesn't quite look legitimate, it's a great way to tackle fraud. And that's deployed in terms of new rules and triggers and real-time systems which detect and stop transactions in these environments. Safety is a really interesting use of AI, because when the challenge is that I want my employees to get home safe, particularly pertinent for mining and heavy industry, the traditional approach has been to use safety data myopically, observations, claims, incidents, and often just looking back at what's happened. But when we take a wider view and merge it with the operational data off the drilling head, what are you going through? How fast are you drilling? Where are you to your financial plan? How have these people been trained? How have they worked together in teams? Taking data from wearables indicative of fatigue, using expense claims to show exorbitant amounts of travel, looking at overtime records, bring the whole thing together in a very highly dimensional system. You start to be able to predict, also using machine learning techniques, where the next incident's going to happen. What crew should I put on this well? What equipment should I use? Who needs training? Who shouldn't be a supervisor anymore? What is working, what isn't working? So it takes safety and incident prevention from a sort of blanket shotgun to being really surgical about the right tools at the right time to improve safety. Another interesting one from the mines is, where should I dig in the first place? And this is again one around feature engineering, where the mine had buried, there's two types of data quite often. There's this scarce and expensive stuff. I've drilled a test well, there was oil there, there was gas there. And there's the plentiful, cheap stuff. I've done a ground-based radar survey, or in this case, it was heaps of little pieces of Gore-Tex buried every couple of hundred metres and then smashed in a mass spectrometer, and the chemical signature was taken out. So we had a couple of hundred hydrocarbons and their relative or their absolute measurements against a little amount of whether there's oil or gas. And the challenge was, how do you take this data and find out where to drill the next well? And this is back to the mine plus machine. I put this into a neural network I sure was going to smash it, and did some cross-validation. It just wasn't bringing it. I couldn't figure it out. But it turned out that it was, I was encoding it incorrectly. I had to change the weights from the absolute picograms of each hydrocarbon to the percentage of the total sample. So not the size of the curve, the shape of the curve. Now the neural net wasn't going to tell me that. We had to twig that as a human way of building that feature, that there might be something in the way blocking a little bit of everything, but the chemical signature you want is the shape, not the size. Once we did that, it was very efficient. A large beverage manufacturer wanted their 50 cents back. And the 50-cent quote is attributed, probably falsely, to Johnny Wanamaker, a famous retailer, who said, "I know 50 cents in every dollar I spend on advertising wasted. I just don't know which 50 cents." The fact is that we can use technology to get that 50 cents back because we know exactly what we advertised, when and where, including through narrowband advertising, although this was looking at all of America, to mark out each micro market with the competitors' presence, exactly what you sold, exactly what they sold, how many marathons were being run, how many obese kids there were, attitudes, TV, even how often that brand was featured when you were watching the basketball and the camera panned past it. We had all of this. It was an enormous model, 12,000, 13,000 metrics, but it was deployed to allow them to do pricing, media mix, exact messaging down to micro MSA segments across America, and has led on to a whole heap of offerings in the advertising and marketing attribution space for the firm. From the Internet of Things, 5,000 sensors in a factory measuring pressure, temperature, flow rates, throughput, hundreds of times a second. What do they do with it? They display it on a centralised control panel. But to really look at what has worked and what hasn't worked, you've got to take all of that data together. And in fact, this led into a bunch of predictive maintenance. What looks like it's going to break down? The fact is, it's not any one sensor that tells you something's going to break. It's the complex interaction between all of them. And that's a great use for machine learning. So I'm running over time. I'm going to skip my last story. We only got through 7. There's plenty more. To recap, the pace of change will never be as slow as it is today, said Matthew Bishop, an editor and writer for The Economist. So given everything's speeding up, given we don't really know what we mean by artificial intelligence, and we've got to be aware of the hype cycle, and it's actually the interaction of AI with things like big data and reverse robotic process automation, the increasing connectivity and emerging technologies like blockchain. Most problems can be solved with this in most industries. The most important takeaway is to follow a process. Identify the challenge, engineer and analyse the data, and make sure you deploy it effectively.